Have you ever looked at a ruler or maybe a digital scale or a stopwatch and just completely trusted the number it gave you? We all tend to think of science and measurement as this realm of absolute, unquestionable precision, right? But what if I told you that every single measurement you have ever taken, or honestly that any scientist has ever recorded, is inherently flawed? Are our measurements ever truly perfect? Well, the short answer is no. And the long answer? That is exactly what we're going to unpack today.
Welcome to This Explainer. Today we're exploring the fascinating, slightly messy, and surprisingly imperfect science of measurement. We're going to look directly at the source material that explains why our tools and our own human senses constantly betray us, just a little bit, every single time we try to measure the physical world. So here is our agenda for today. First, we'll cover the myth of perfection. Second, unpacking human errors. Third, spotting systematic errors. Fourth, dealing with random errors. And finally, number 5, we'll test your knowledge. Let's get right into it.
Starting things off with Section 1, the myth of perfection. Okay, let's dive into this foundational concept, because the source material establishes a pretty hard truth right away. Measurements using tools and instruments are literally never perfect. Whenever you measure something, the value you get will always differ from the object's absolute true value. They inherit errors. So you might be wondering, if perfection is impossible, what are scientists actually doing out there? Well, the goal kind of shifts. A scientist's job isn't to be perfect, it's to ensure that the errors are as small as reasonably possible. It's an ongoing battle of damage control, not a quest for absolute flawlessness. In fact, any good scientific measurement will actually indicate its estimated error right alongside the value.
So where do these unavoidable errors actually come from? Let's move to Section 2. Unpacking human errors.
It turns out our own physical limitations play a huge role in measurement. Human errors, which are sometimes called personal errors, happen just because of our own physical performance. Think about a high school track meet. You've got a coach standing at the finish line with a stopwatch. When the runner crosses the line, the coach clicks the button. But there is a biological delay, a reaction time between the coach's eyes seeing the runner cross, the brain processing that information, and the finger actually pressing the button. That tiny fraction of a second completely alters the measured value. The runner's true time is obscured by the literal limitations of the human operating the clock.
And hey, it's not just reaction times, it's also faulty procedures and just human perception. Let's look at a super relatable everyday example. Imagine you're baking a cake and you need exactly 1 cup of milk. You pour the milk into a glass measuring jug sitting on the counter. If you stand right above the jug and look down at an angle, the liquid might look like it's exactly at the 1 cup line. But if you crouch down and line your eye up directly horizontally with the level of the liquid, you'll suddenly see it's actually way over the line. This inability to perfectly estimate a pointer on a scale just by moving your head is a classic personal error.
So, the absolutely crucial question is, how do we fix ourselves? The text gives us a really clear roadmap here. Step 1 is proper training, like literally teaching someone the right technique, such as crouching down to read that measuring cup at eye level. Step 2 is avoiding environmental distractions so the person can actually focus. But Step 3 is the ultimate fix. Use automated or digital instruments. If you want to eliminate human reaction time at that track meet, you just replace the coach's thumb with an automated laser sensor at the finish line. You just take the human out of the equation entirely. Problem solved.
But what happens when the human does everything perfectly and the data is still wrong? That brings us to Section 3, spotting systematic errors.
Unlike a human error, which might be a bit messy or inconsistent, a systematic error is incredibly stubborn. It influences all measurements of a particular quantity equally. It produces a consistent difference in reading. It basically follows a definite rule. If you're measuring a block of wood 10 times, a systematic error won't give you 10 wildly different numbers. It's going to give you 10 numbers that are all exactly 2 millimeters too long.
And the core reason systematic errors happen is pretty simple. The equipment is to blame. The text highlights a few main causes. There's zero error, which is like a bathroom scale that reads 5 pounds when absolutely nobody is standing on it. If you step on it, your weight will automatically be measured 5 pounds heavier than your true value, every single time. There's also poor calibration or incorrect markings. Imagine a wooden ruler where the printing press just messed up and the millimeter lines are slightly too far apart, or maybe the physical end of the ruler got chipped away. Every single measurement taken with that specific tool will be systematically skewed.
Fortunately, because systematic errors are so predictable, they are totally mathematically fixable. As the source material states, you can reduce this error by comparing your faulty instrument with one that is known to be perfectly accurate. If you realize your bathroom scale is consistently starting at 5 pounds, you simply subtract 5 pounds from whatever number it gives you. That subtraction is called a correction factor. You apply it to all your readings, and boom, you've completely neutralized the systematic error.
Okay, we've fixed the humans and we've fixed the broken tools. We should be totally good now, right? Well, not quite. Let's look at Section 4, Dealing with Random Errors.
This is where the universe itself seems to just plot against our measurements. Random errors occur when you repeat a measurement under the exact same conditions, but you still get slightly different values. Why? Because of unknown, wildly unpredictable causes. The experimenter has almost no control over this. The text points to sudden fluctuations in the environment. Maybe you're using a highly sensitive digital scale to measure a tiny amount of chemicals, and someone opens a door down the hall, causing a microscopic change in air pressure. Or a slight voltage variation in the wall outlet causes the digital display to flicker. Or even a tiny change in room humidity affects the moisture weight of the sample. It is pure, unpredictable chaos.
Because you can't predict random errors, you can't just apply a simple correction factor like before. Instead, you have to use the power of averages. The source provides a classic physics example, measuring the time period of an oscillating pendulum. A weight swinging back and forth on a string. Instead of timing just one single swing, which could be completely thrown off by a sudden draft of air, you time several oscillations, say 30 of them in a row. By taking multiple readings and calculating the mean or average value, those tiny unpredictable environmental spikes basically cancel each other out. The average gets you so much closer to the true value than any single isolated measurement ever could.
So, we've covered the three big types: human, systematic, and random. Let's see how well you can spot them in the wild. Welcome to Section 5. Test your knowledge.
The source material includes a fantastic quick quiz to identify personal, systematic, and random errors based on real scenarios. I want you to actively think about these as I read them. Scenario 1. Your eye level moves a bit while reading the meniscus, that curved surface of a liquid in a tube. Scenario 2. A sudden air current causes your balancing scale to fluctuate. Scenario 3. The balance you are using may not be properly calibrated. Scenario 4. Some of the liquid you are measuring may have evaporated while it is being measured. How would you categorize these? Have your answers ready?
All right, let's reveal the answers and see how you did. For Scenario 1, moving your eye level is a textbook personal or human error, purely based on the observer's technique. Scenario 2, an unpredictable air current, is absolutely a random error, an environmental fluctuation totally out of your control. Scenario 3, a poorly calibrated balance, is a systematic error. It's built right into the tool and will consistently skew every reading the exact same way. And finally, Scenario 4, liquid evaporating during measurement, is another tricky, random error, as it introduces an uncontrollable environmental variable that subtly changes over the course of the experiment.
Which brings us to a final, slightly mind-bending thought to wrap up this explainer. We just learned that through human flaws, faulty tools, and the unpredictable chaos of the environment, true perfection in measurement is quite literally a myth. The entire goal is just to minimize the errors. So if all measurements are inherently flawed, how much of our incredibly advanced modern world, from the massive skyscrapers we live in, to the smartphones in our pockets,